Okay. So, while we were discussing the spin, we just went on with more stuff associated with angular momentum, which we have more or less finalized. And now what we'll have to do is go back to the three-dimensional solution, okay, the three-dimensional Schrödinger equation solutions, and we came to a certain point in that discussion, but we never solved the radial equation. Okay, so we only looked at the angular part, which was related to the angular momentum. So we had this, okay, Schrödinger equation, which said the kinetic energy part plus V of R, okay, psi is equal to E psi. Now, when we expanded this piece, okay, in spherical coordinates, we had this minus h bar squared over 2m, and there is this radial part, which I hope I'll remember correctly. I'll just check this in a minute. Okay, so this is the radial part, if I remember correctly. Let's check that, because if I make a mistake at this point, we'll have no hope of getting anything that makes sense. Yes, well, amazing, but it's true. Okay, so plus, okay, we had the angular part, which we could write as L squared over 2 m r squared, right? So an easy way to remember that term is just look at the classical term, and it's actually the same thing. If you have some mass rotating around some center with some velocity v, the angular momentum is mvr, okay? And so if you look at L squared, it becomes m squared v squared r squared. So if you look at L squared over 2 mr squared, it then becomes 1 over 2 mv squared. Okay, so it's a classical sort of calculation, but gives you the correct term in this term also. Okay, so L squared is the angular part. So this is the part that contains the theta and the phi derivatives. Okay, and then I have plus V of R. Remember, this R cannot contain any theta or phi, otherwise I cannot do separation of variables. Okay, so all of this is the left-hand side of the Schrödinger equation. Psi is equal to E psi. Then we did a separation of variables. Okay, so if you do a separation of variables, okay, so what we did was we said, okay, suppose this R of theta, R theta and phi can be written as some radial function R of R, and the angular function, we found out that the eigenstates were in the form of YLM of theta and phi. So these were the spherical harmonics, right? And the spherical harmonics correspond to what we are calling these LMs, okay, in Dirac notation. So L squared Y LM gave us H bar squared L plus 1 times YLM. Okay, so we have this eigenstate, okay, condition. So if I now put this psi into my equation, what do I get? Well, first of all, YLMs will just, factor out, and I'll be left with just the radial equation. So I'll get minus h bar squared over 2m, 1 over r squared, del r. Well, no longer partial derivatives. I can have these things as ordinary derivatives because I'll be differentiating r, capital R only, r squared dr, times YLM, but YLM will be present in all of the terms, so I'm going to cancel them. Then plus the numerator here is going to be L plus 1 times h bar squared divided by 2m r squared times r of r, plus v of r of r is equal to energy r of r. So this is the form of the Schrödinger equation when I factor out the angular dependence. What did I do with my eraser? All right, so what I am going to do next is to use a trick. And set, so I'm going to set r of r equal to u divided by r. So this is going to be some other function. Just make that substitution into that equation. So obviously almost nothing changes in the equation except that I have this derivative term. So let's work out that derivative term. So I'm going to get dr is going to be u prime over r
minus u over r squared.
U over r squared. Very good. But I'm also multiplying by r squared, so r squared dr is r u prime minus u. Then one more derivative, so dr of r squared dr is going to be u prime plus r u double prime minus u prime. So these u primes cancel, which will provide some simplification. And finally, let me just write it 1 over r squared dr r squared dr will be equal to u double prime over r. So let me substitute that into my equation. So minus h bar squared over 2m, 1 over r d squared u dr squared, plus L plus 1 h bar squared over 2m r squared, and in place of r I'm going to put a u over r, plus the potential times u over r is equal to E u over r. And you see there's a 1 over r in each one of these terms, so I just cancel them. So you get a somewhat interesting equation minus h bar squared over 2m d squared u dr squared. So this is just like the one-dimensional Schrödinger equation, right? So it's a one-dimensional Schrödinger equation. And then you have this term L plus 1 times h bar squared over 2m r squared plus v of r, okay, times u is equal to eu. Okay, so it's just the one-dimensional Schrödinger equation, as if the particle is moving in r. Obviously, you have to be careful because r here is from 0 to infinity, right? There's no sense in discussing negative radii because it's covered in theta and phi. So you have to be careful about the boundary condition at 0. But apart from that, it's a one-dimensional Schrödinger equation. And I have this potential which takes care of the potential in the radial direction. We said that there's no angular dependence. This term is associated with the angular momentum. So depending on what the angular momentum is, you have some term here which is positive, which means it pushes the electron away from the center. Okay, so this term is called the centrifugal term. Centrifugal term. So it's as if there is some additional potential due to angular motion, which is pushing the electron away from the center. If L is equal to 0, this term disappears. And in fact, the problem becomes usually much easier because it's 1 over r squared term. Okay, it will generate complications. Okay, so that's the radial Schrödinger equation. Okay, so this is called radial Schrödinger equation. Okay, so now this is the problem that we are faced with. We want to solve problems which are associated with different values of V of r. So the simplest thing that we can do is we can look at the particle in a box problem. Okay, so before we attack the hydrogen atom problem, so let me call this example. Okay, particle in a spherical box. Okay, which really means a ball, right? Okay, so what do I have? I have a particle inside some radius. So suppose this is some radius a. Okay, these are the x, y, z directions. But the potential is given such that the potential is infinite. You could take finite potential, obviously. That will be a more complicated problem. But if you just take a V of r is equal to 0 for r less than a and infinite for r greater than a, then I have this particle which has to stay in this spherical box. Okay, so it's a spherical quantum dot, if you like. Okay, so in the region of interest, this V of r is 0. So I get an equation which says minus h bar squared over 2m d squared u d r squared. Remember that once we find u, we have to go back to the radial function r of r, okay, to evaluate expectation values or things like that. But this is a simpler equation to work with. So then V of r is 0, but I have L plus 1 h bar squared divided by 2m r squared u, right, is equal to EU. All right, so we need to solve this problem. Let me, in fact, just rearrange terms so that I'm going to get d squared u dr squared is equal to what? 2me over h bar squared. Okay, with a minus sign, u, and then I'm going to get also something with a plus sign, l plus 1, right, 2m over h bar squared is gone, so please check my algebra, r squared u. Okay, so that's what the equation looks like. Now, if L is not 0, then this the solution to this equation is a set of special functions called the spherical Bessel functions. But let's discuss the L equal to 0 case, because intuitively that tells us a lot also. Okay, so let's look at the L equal to 0 case first. Then it's very simple, right? We return to the first weeks of last semester, minus 2me over h bar squared. In fact, let me just call it k squared. K squared u, where k squared is 2me over h bar squared. Okay, and the solutions are very simple, right? So solutions are going to be, yes, linear combination of sine kr and cosine kr. Now, we have to look at a little carefully again at the boundary condition, because at r equal to 0, we have interesting things happening. So let me remind you that our wave function is going to be u of r over r, okay? And I don't want anything that diverges at r going to 0. And not only that, but if you look at the wave function, so if I just look at along any axis, I have the origin, okay, and minus a and a are the, okay, boundaries of the sphere. Now I'm going to get a wave function which I want it to go to 0 at x equal to plus or minus a, but also I want it to behave properly over here, because I don't want current, okay, doing silly things. The derivative of that, etc., must be well behaved. Otherwise, I'm going to get problems with the probability current at r equal to 0. Okay, so although r equal to 0 is some sort of, okay, strange singular point in spherical coordinates, in ordinary space, obviously, it has no important significance. Okay, so I don't want divergences at r equal to 0, so I don't want the cosine term. And I want the function to go to 0. Okay, so this is the x-axis, but r starts from 0 and goes in that direction. So sine kr over r will be well behaved. Okay, so that means that I'm going to get this u of r is going to be equal to what? Some normalization sine n pi over a r, right? So I want that will guarantee that for n equal to 1, 2, 3, etc., the boundary condition at r equal to a is, yes, satisfied.
Hocam, why did we cross out the cosine term? Because cosine over r would be 0 in the limits r goes to 0.
No, cosine over r would diverge. Cosine goes to 1, right?
Oh, yes.
Okay, but sine is safe. Okay. So if you look at your textbook, there is some discussion about how cosine might sneak into this discussion, because you have this cosine kr over r, which is going small r, which is going to be the wave function. So if you look at the wave function squared, if you want to normalize it, this is what you have, okay? And then if you want to normalize this, obviously you have to multiply this thing by what? R squared dr and the angular integral. Okay, so you may get away with cosine in terms of normalization. So normalization is not that much of a problem, but
But it can satisfy the boundary conditions.
yes, the probability current boundary condition there is more strict. Okay, so that's why we don't include it.
So the non-singularity of the wave function only holds for Cartesian coordinates. And in curvilinear coordinates, there might be cases where singularities happen.
Well, it depends. You see, the singularity here does cause us a problem, so we exclude this function. Okay, from the point of view of normalization, okay, you can get away with it, but normalization is not your only worry. Okay, so you have to make sure that you have finite probability currents, etc. In fact, you want zero probability current for a stationary state. Okay. So, okay, that's that. We can try normalizing this and such things, but it's not too, nothing too exciting there. Let's look at the energies. So I have this k squared, which is going to be equal to n squared pi squared over a squared is going to be 2me over h bar squared. Okay, so let me put a subscript n on the energy. So those are the energy levels. So En is going to be h bar squared over 2m, and then you have this pi squared over a squared, then n squared. Okay, so these are the energy levels. Let's perhaps compare this with a cubic quantum well. Okay, so this is my particle in a box, in a spherical box. Okay, so what would happen if I put the particle not into the sphere but into a cubic box, which just sort of encloses that sphere? Okay, so the radius of the sphere is a. Suppose I have 2a by 2a by 2a cubic box. Okay, so this is for the spherical case. sphere with radius A. Now, what would happen if I had a cube with side 2A? Because that would sort of be comparable to the sphere. Okay, so that's going to be h bar squared over 2m, right? Divided by, okay, multiplied by pi squared over 2a squared, because that's the size of the box, right? And this is the energy of the eigenstate in only one direction, but I have 3 directions, so I have to multiply it with 3. So that would be the En for the cubic box, right? So in this case, I solved the Schrödinger equation separately for those 3 directions, and that's what I get. Okay, so it's almost the same. You see I have pi squared over a squared here. Here I have the same object, pi squared over a squared, but I have a factor 3 over 4. Okay. So this is a little lower energy. Why is that? Because it's a bigger box. Okay. It's just a little bit bigger box, so it's just confined to a it's confined to a smaller volume, then the energy just increases a little bit. All right. So let's now go back to our equation and let's see what happens. All right, so this thing I called k squared, so let me just put it over here. That's my eraser. Okay, so this was the case of the electron just sitting at the origin, not carrying out any rotation, 0 angular momentum. If L is not equal to 0, then we have to work with a different equation. We have d squared u, d r squared is equal to minus k squared u. Okay, so it's the L equal to 0 case. Then I have L plus 1 divided by r squared u. Okay, so the solutions to this, we are not going to go through the solution of the problem. The solutions result in spherical Bessel functions, but these functions also come up in various other topics, especially the scattering problems, also in electromagnetism. So usually the properties are covered more when they are used more. We are just going to state them and not really go into much more detail. So the okay. So the solutions to this equation are, okay, let me make sure I put down everything correctly. Okay, R times J sub L of K R. Okay, so they are functions which look like this, and there's also an NL of K R. And I have linear combinations of these things. So you see the R function actually just drops these radial functions. So the R of R's are these JL and L's directly. Since we know the solution to L equal to 0, you can guess what J0 is, right? So since, okay, so J0 or KR, you can see what that is, okay, because R times JL is going to give me sine KR, so this is proportional to sine KR over R, okay? And you see it's for small r, it goes like a constant. So in general, JL of KR goes like R to the L, or small l.
K for small r, because sine KR would be KR.
Yeah, it's just proportional, okay? Proportional, I don't care about constants. Okay, NL, the other version of KR goes like R to the minus L or something, R to the minus L minus 1 or something like that. Okay, so it's something that diverges, so it's just like the coefficients, the stuff that we have over here, so you don't want that. Okay, what do these functions look like? Let me just, at least for some amount of completeness, try to give you what these things are. Yeah, okay. So, JL of KR is equal to minus x to the L 1 over x d dx L's power, it's JL of x, sorry, sine x over x. Okay, so obviously if L is equal to 0, you get sine KR over R. Should I write the NL? Yeah, let's just do that. NL of x, on the other hand, is minus x to the L 1 over x d dx cosine to the L power cosine x over x. Okay, so these are called the spherical Bessel functions. They are related to the ordinary Bessel functions with fractional indices. Okay, what else do I want to say? Well, how do these things behave? Semi-quantitatively. If I plot them as a function of x, okay, so it's going to be the JL of x's. So J0 is something which does something like that, okay? It goes like sine KR over R, so it's a constant, but then it decays like 1 over R oscillating. J1 starts out linearly and does something like this. Okay, J squared, so this is J.
It should start at, shouldn't J1 start at 1?
No. No, it goes like x to the 1. Okay. So this is J0, J1, J2 starts quadratically and does something like that, okay, roughly, obviously. Now, in the case of, okay, the L equal to 0 term, remember we have to get these sine functions to fit into the sphere. Okay, so we take certain values of the sine so that we make sure that the sine function goes to 0 at the boundary. Now, instead of the sine functions, we have these JL functions, and we want to fit them into the box so that, okay, their zeros correspond to the boundary. Now, these things have names. Okay, so this, for example, is called beta 0, 0. Okay, that number is the root of the 0th order, I'm sorry, other way around. It's the first root of the 0th order spherical Bessel function. So if I just follow this curve over here, this point here is called beta 2, 0. And this one is beta 3, 0, and so on. Okay? And then if I look at this one, for example, this point here is beta first 0 of first Bessel function. Just follow it through. This one here is the second root of first beta function, and so on. Okay, so I can label these things, the zeros of the Bessel functions like that. Okay, so these are used by people who are doing the separation of variables for various purposes. And again, you have both computer code and tables available to look these things up if you actually need them. Now, we want actually, okay, we want JL of KR, K at A, okay, equal to 0. We want the wave function U at, okay, because this is equal to U at A, right, is equal to this. So how do I accomplish that? Well, I put in place of K something which is related to beta so that it makes it equal to 0. Okay, so I put in place of K a beta, okay, NL. Okay, nth root of the L Bessel function. Okay, so if I do that, then what do I get? Well, my energy is K squared, so my energy is equal to H bar squared K squared over 2m. So that means now I have to put an index. That means that energy or the nth level, okay, for the corresponding angular momentum index, L, is equal to H bar squared beta and L squared, I'm sorry, I have to put in beta and L over A, right, for K, so that I get a 0 there. Okay, and then I have 2m A squared.
So how do they behave asymptotically?
Well, asymptotically they behave like the sine waves as you get larger and larger. Okay, the asymptotic behavior for large r just becomes sine kr over r.
No, I mean, how does beta and L behave asymptotically?
Well, it behaves like the roots for the sine function, right? So it goes like n pi over a or something with some phase shift possibly. All right, so these are the energy eigenvalues. This n is called the energy quantum number. Okay, and this L is the angular momentum quantum number. Okay, so what am I going to get for the energy levels? The lowest energy level is going to be the case for the L equal to 0. Okay, so this is going to be n, first one for L equal to 0. This is the one that we calculated when L was equal to 0. Now, since L is equal to 0, this corresponds to an energy level with n equal to 1, but L equal to 0, and m has to be 0, right? There's also another index m which doesn't go into the energy equation, but it's there, okay, because I have angular momentum eigenfunction. So it's n equal to 1, L equal to 0, m equal to 0. Then I have other stuff. Okay, so somewhere over here I cannot really make out how the ordering will go because of the non-uniform distribution of these betas. But suppose I'm going to get some energy level here which corresponds to E n L. So that's some general energy level. And what happens is that I'm going to get an energy level which corresponds to n equal to 0. Okay, and I am going to have some L, but I'm also going to have some m, which can start from plus L, L minus 1, all the way down to minus L. Okay, so these energy levels will be degenerate. Okay, so there will be a degeneracy based on what L is. Okay, so it's not going to be a single energy level. Now that is, okay, so suppose I have lots of energy levels like that, okay? And they have different degrees of degeneracies. Now, why do we have these degeneracies? They all have different values of m. Okay, so they have the same energies, but the z component of the angular momentum is different for different states. Now, that means the magnetic moment of the system is different for all of these states. It doesn't make any difference in the energy because there is no effect here which will influence the energy. But suppose I put a magnetic field on the system. Now, if I put a magnetic field on the system, each one of these things will have different energies, right? So what will happen? These things will start splitting up. Okay, so you are going to get different energies here corresponding to different z components of the angular momentum. Now, how do we analyze systems like this? How much time do we have? Okay, so the way we analyze these systems is, okay, we excite electrons to these states and then they decay back to lower energy states. Right? And you look at the light that comes out, which corresponds to the energy difference. So if I plot the frequency, okay, of light, so this is h bar omega energy is going out. So if I plot the amount of intensity of light that comes out of the system, I'm going to get a certain nice, very sharp peak corresponding to this energy. But if I apply the magnetic field, then this becomes, okay, not a single line, but a bunch of lines. And depending on what probabilities for transition you have, you are going to get different amounts of split. Okay, so this is called spectrography, and it's a very important tool for studying materials. And the higher quality spectrographs will obviously be able to see those splittings with more and more accuracy. So this event is called energy level splitting. Okay, the splitting here is the energy levels just gets certain different values, and they when they fall into the lower energy level, the light that comes out is no longer a single wavelength, single frequency, but you have a bunch of different possibilities. Okay, so if you go to the physics department seminars, for example, people who are working in energy levels and such things, they always refer to these things, and obviously I have exaggerated this somewhat. Usually there will be just 2 or 3 peaks, okay, associated with the splitting, and then they'll say, okay, this splits under the magnetic field like this, or it may split due to some other effect. Okay, so you have this quantum dot. You assume that it's something that's isolated, there's no magnetic field, etc. But perhaps there's something next to it, okay, some nucleus or electron, etc., which is producing some field at the position of that quantum dot, and you see the splitting. So that gives you a hint about what may be going on around the quantum dot. Okay, that perhaps you have something, some effect, which is generating a magnetic field. Okay, so let's see, do I want to say anything else about this? All right, probably not. So the next thing that we are going to attack is the hydrogen atom. And I'm not sure if I have enough time to start the discussion. Well, maybe yes. Okay, so let's look at the hydrogen atom. So obviously we cannot finish all of the discussion, but at least we'll scale the equation and such things. All right. So let me just also pass this around before I forget. Okay, thank you. So we have our equation, and very easy to remember. Minus h bar squared over 2m, we just write the one-dimensional Schrödinger equation. E squared u dr squared, plus we have a centrifugal term, which is L plus 1 times h bar squared divided by 2m r. And then the term which really defines the model is the Coulomb interaction. Okay, so it's attractive minus sign. And I'm going to get here what? E squared over 4 pi epsilon 0 r. So I have the proton fixed at the origin. This is the potential energy associated with the electron, right? So this is multiplied by u is equal to EU. Okay, so this is the equation that I want to solve. Okay? Now, we can obviously go ahead and solve it with these variables and everything, but it is customary to divide this equation into some quantity so that you get mostly unitless variables. You see, I have u multiplying everything here, and there's energy here. So, what did I forget?
It's supposed to be r squared.
R squared, yes, thank you. Okay, so all terms here which are multiplying the U must have units of energy, right? So what I can do is I can divide everything by E and obtain a new equation. Now, let me just do that.
Clump, that is also r squared.
No, that's the force.
Oh, okay, okay.
This is the potential, right? Okay, so d squared, so I'm dividing by E, so I get an E here. D squared U d r squared plus L plus 1 h bar squared 2 m E r squared, okay, minus E squared or 4 pi epsilon 0 E r, U is equal to U. Okay, now that I have divided everything by energy, everything should be unitless. Now, what I do is I define some quantity here, which I am going to call 1 over k squared, so that I have something like this, 1 over k squared du d squared u dr squared. So that will be the first term. Now, one warning, let me go all the way over here. I need to have, so this is my potential as a function of r. V is something which goes like this. So I'm going to get, I'm interested in bound states. I may also be interested in scattering states. If I want scatter an electron from a proton, right, that's a scattering problem. So if so the energies that are less than 0 here are the bound state problem, but I can also shoot an electron from some place and see how it goes, how it scatters, in which direction it scatters. It's a three-dimensional problem now, okay? And look at the direction that it scatters, and that will be a scattering problem. So in this discussion, we'll mainly be interested in the bound states. Okay, so the bound state means that E is negative. Okay, E is less than 0. So this term here is actually greater than 0. So what I have done is I have chosen a k squared, which is equal to minus 2me over h bar squared. This is something that we'll need. Okay, so if I do that, that's what I get. Plus, okay, I have this term, which is L plus 1 h bar squared divided by, 2m. In place of E, let me put in this value, okay? So E is going to be minus h bar squared k squared over 2m. Okay, so I'm going to put that here, minus h bar squared k squared over 2m. That's my E, r squared. Okay, minus E squared, okay, divided by 4 pi epsilon 0. Let me again do the same thing, minus h bar squared k squared over 2m, okay, times r. Okay, all of that times u is equal to u. So let me just go through this. Now what I'm going to do is, you see, I said I'm going to divide everything by energy to get unitless terms. But this k is a wave number, so it has units of 1 over distance, right? So together with r, it makes a unitless quantity. So I'm going to define a unitless distance measure, k times r. So now we have another equation, d squared u d rho squared, okay, plus I have, okay, you see almost everything cancels here. H bar squared cancel, k squared and r squared form a rho squared. M's go away, but there's a minus sign. So minus L plus 1 over rho squared. Okay, finally this last term, which is going to be plus, because I have a minus here, E squared over, okay, there's a 2m in the numerator, 4 pi epsilon 0 h bar squared. Please check my algebra. Okay, k times r is just one factor of rho, so I have a k rho. All right. And I have, if I move the other u to this side, it's going to be a minus 1. U is 0. Okay, so this has simplified quite a bit. In fact, this term here contains all of the physics, right? This is the angular momentum term. This just came from the right-hand side of the Schrödinger equation. Okay, this is the kinetic energy term, so those are all standard things. The only thing that makes difference from one model to other, but what makes this a model for hydrogen atom is this term here, okay? So that's why it contains all these physical parameters. So, one last line, d squared u d rho squared, okay? And then I have this term, let me give all of that stuff a name, rho 0 over rho, minus 1 minus L plus 1 divided by rho squared u equals 0, where this rho 0 is this term here, e squared m over 2 pi epsilon 0 h bar squared k. Okay, so these things we'll have to remember at the end of the calculation. While we are doing the calculation, okay, this is our now much simplified or simpler looking equation. It's really actually the same thing except that the variables have been scaled. Okay, there's an advantage to scaling, there's a plus sign here. There's an advantage to scaling the equation because you work with, okay, a simpler set of variables. The disadvantage is you lose all units. This is now completely unitless, and if you cannot do checking units as you do your algebra, okay? So since everything is unitless, there's no way to say that this is right or wrong.
I have a question.
Yes.
Here we wrote rho 0 like it's a constant, but it depends on k, which depends on energy. So shouldn't it have an index?
It will eventually, okay? So at this point we are just keeping it as E. Obviously E will be quantized at the end of the problem. Okay, I'll let you go and we'll meet sometime next week.